So good morning. First year Bcom, Computer Applications, Semester 1, FIT, UNIT-2, Number Systems. First year Bcom Computer Applications, Semester 1, UNIT-2, FIT, Number Systems. We start with another PPT. So what are the different types of number systems and how to convert from one number system to another number system. So counting and arithmetic, generally decimal or base 10 number system, origin is counting on the figures, digit from the Latin word. Base means the number of digits, the number of different digits including 0 in the number system. Example, base 10 has 10 digits 0 through 9. Binary or base 2 bit have bits means binary digits, having bits or binary digits. So binary digits means bits. So binary number system have base 2 or generally they are using bits or binary digits. There are only 2 digits, 0 and 1. Next is third one is octal number system or octal or base 8, having 8 digits from 0 through 7. 0 through 7 means total 8 digits. And one more 1.2 noted here is all the number systems means all the 4 number systems, decimal, hexadecimal, octal and binary number systems should starts with 0. So octal, third number system is octal or base 8 number system, have 8 digits on it, that is 0 through 7. Hexadecimal or base 16, hexadecimal or base 16 have 16 digits in it, and from 0 through F, 0 to 9 are total 10. And decimal 10 means capital A, decimal 11 means capital B, decimal 12 means capital C, decimal 13 means capital D, decimal 14 means capital E, decimal 15 means capital F. So hexadecimal or base 16 number system have 16 digits, that is from 0 through capital F. Hexadecimal example is decimal 10. Decimal 10 in hexadecimal means decimal 10 is capital A in hexadecimal. Similarly, decimal 11 means capital B in hexadecimal. So why binary? Early computers designed with decimal mark 1 and ENIAC. John von Neumann proposed binary data processing, simplified computer design used for both instructions and data. So generally from the beginning onwards, in the beginning we may use a decimal number system, and later it will convert it into binary number systems. So all the computers are built up with binary number, uses binary number system only, that is 0 and 1. Binary number system has 2 digits, 0 and 1. 0 means power off or off, false, no. All these things are used for zeros. 0 means binary, 0 means power off, false, no. Non-zero, all non-zero means 1. 1 means yes, true or on. We signal. So these two are electrical signals. The electrical and electronic signals, we may use these components. Next, keeping track of the bits. So bits commonly stored and manipulated in groups. Generally 8 bits are called as 1 byte and 4 bytes are called as 1 word in many systems. Number of bits used in calculations actually affects accuracy of the results, limit, size and range of numbers. So numbers, physical representation, different numbers, same number of oranges. So positional notation. So what is positional notation of base 2 or positional notation of base 10? For example, positional notation means how a number is formed. How a number is formed by using its own decimal number, by decimal system, by using its own decimal system. So for example, decimal 527, decimal 527 is formed or formatted in like this. So the original or base or index of decimal number system is 10. So starting from extreme right digit, that is 7. So starting with 7 into the original base is 10. So 7 into 2 10 power 0 plus second digit is 2 into 10 power 1 and plus third digit is 5 into 10 square. So this type of calculation is called as positional notation. So 10 power 0 means 10, 1 and 10 power 1 means 1 and 10 square means 100. So 500 plus 20 plus 7, that is 527. So this is the explanation of using positional notations. So place, value and evaluate and sum. So this is called as a positional notation of base 10. Next is octal. So how to use positional notations in octal number system? For example, decimal 624, octal 624 is equivalent to decimal 404. Octal 624 is equals to decimal 404. How it is converted means so 4 starting from extreme right digit, that is 4 into the original base is 8. So 4 into 8 power 0 plus 2 into 8 power 1 plus 6 into 8 square. So 4 into 8 power 0 means 1, 8 power 1 means 8, that is value 8 square means 64. So place, value, evaluate, sum for base 10. So 1 into 4 and 2 into 8 and so starting from extreme right, 4 into 1 plus 2 into 8 plus 6 into 8 square means 6 into 64, that is 4 plus 16 plus 384, that is 404. So positional notation for hexadecimal. So how to use positional notations for hexadecimal number system? So convert 6704 hexadecimal into equivalent decimal place. So starting from extreme right digit, that is 4 into 16 power 0 plus 0 into 16 power 1 plus 7 into 16 square plus 6 into 16 cube. So total is 26,372. So positional notation for binary number systems or binary. So how to use positional number system? So 1 take some binary number 1101 0110 of binary, and what is the equivalent number, decimal equivalent of this binary number. So taking from, so the original the base or index value of binary number system is 2. So taking from extreme right digit, that is 2. So 0 into 2 power 0, starting with 2 power 0, 2 power 0, 2 power 1. So place is 2 power 0, 2 power 1, 2 power 2 square, 2 cube, 2 power 4, 2 power 5, like that. And so 2 power 0 is 1, 2 power 1 means 2, 2 square is 4, 2 cube is 8, 2 power 4 is 16, 2 power 5 is 32, 2 power 6 is 64 and 2 power 7 is 128. So evaluate. How to evaluate? Starting from extreme right digit, that is 0. So 0 into So 0 into 1 plus 1 into 2 plus 1 into 4 plus 0 into 8 plus 1 into 16 plus 0 into 32 plus 1 into 64 plus 1 into 128. So the total is 214. That is binary equivalent of 1101 0110 is equivalent to decimal equivalent is 214 of decimal equivalent. So range of possible numbers. So how to find out ranges of possible numbers? Means r is equals to b power k, where r is equals to range, b means base, k is number of digits. So here take first example, base 10, 2 digits, means r is equals to 10 square, that is equal to 100 different numbers. Example 2, base 2, 16 digits, means range is equals to 2 power 16. So 65536 or 64,000. So 16-bit number can represent 65536 different number values. So decimal ranges for bit is. So what are the different number bases and number systems? What are the different number bases and number systems used? So base, what is the base or index? The number of different symbols required, the number of decimal, the number of different symbols required to represent any given number. So what is a base or index? The number of different symbols required to represent any given number. The larger the base, the more symbols are required. So for example, the larger the base, the more symbols are required. Means base 10 or index 10 means 10 digits, 0 to 9. Base 2 R2 used only 2 digits, and base 8 means octal used only 8 digits, that is 0 to 7, and base 16 means total 16 digits, used 0 to F, 0 to 9, and capital A, capital B, capital C, capital D, capital E, capital F. So number of symbols versus number of digits. Number of symbols versus number of digits. So for a given number, the larger the base, the more symbols required, but the fewer digits needed. Example 1, 65, hexadecimal 65, and decimal 101, and octal 145, and 110, 01, 001 octal. So addition. So how to add, how to perform additions, subtractions, multiplications in various number systems. So how to perform or how to do additions or some subtractions, multiplications of various numbers in various number systems. So base, binary, hexadecimal, octal, and decimal. So for example, decimal 6 and 3 means 9. Octal 6 plus 1 means it is 7. Hexadecimal 6 plus 9. Hexadecimal 6 plus 9 means it is 15. Hexadecimal 6 plus 9 means it is 15. But there is no direct number in 15, so it is coded as capital F. So capital A is 10, capital B for 11, capital C for 12, capital D for 13, capital E for 14, capital F for 15. So hexadecimal 6 plus 9 means capital F. Binary 1 plus 0 means 1. Next, decimal 6 plus 4 means 10. Octal 6 plus 2 means 8. 8, there is no digit 8 in the hexadecimal octal number system, so simply divide it by 7. So when you divide it 8 by 7, the quotient is 1, remainder is 0, so the digit is 1 0. So when you perform addition of two octal numbers 6 plus 2, the answer is 1 0. Hexadecimal. Next, add hexadecimal 6 plus a. What is a? A means 10. So 10 plus 6, that is 16. That is 16. So in the hexadecimal notation, you simply divide 16 by 16, that is 1 0. What is 1 plus 1? 1 plus 1 means 1 0. 1 plus 1 means sum is 0, it carries 1. Sum is 0 and carries 1. So binary arithmetic. What is arithmetic? Arithmetic means doing some additions, subtractions, divisions, multiplications, like that. So how to add 1 1 0, 1 1 0 1 2, 1 0 1 1 1 0. So first write these two numbers spaciously by giving some spaces in between digits on a paper and count. 1 plus 0 means 1, 0 plus 1 means 1, 1 plus 1 means 1 0. We know that 1 plus 1 is 1 0. So here the sum is 0 and carries 1. So write the sum part, that is 0, and carry forward to the next digit. So here we may add 1 1 0. Here we require to add 1 1 0. What is 1 plus 1? That is 1 0, plus 0 means 1 0 only. So some part is 0 and this part is 1. So again 1. Add 1 0 1. That is 1 0. Sum is 0, carries 1. So 1 1. 1 plus 1 means add again 1 plus 1 is 1 0. Sum is 0 and carry 1, like that 0 1. So what is the sum of these two numbers? 1 1 0 1 1 0 1 plus 1 0 1 1 0 is 1 0 0 0 0 0 1 1. So it is called as a binary arithmetic. Means what is arithmetic? Means doing some calculations or additions, calculations or subtractions on these numbers. So next is addition, Boolean using XOR and so here again we start with converting from base 10 or converting from decimal system, that is base 10. And how to converting from base 10 to base 2, from base 10 to base 2. So here it is a simple process how to convert a decimal number system or base 10 to a binary number system, that is a base 2. So here it is the simple process or a calculation how to convert a decimal number system to binary number system, that is base 10 to base 2. So take some example 42. Base 10, convert 42, that is base 10 to base 2. So simply take 42 as a decimal number and convert it by divided it by 2. Divided, why? Because we want to convert it into decimal 2, binary 2 or binary number system. So decimal to binary means you simply divide it, the given decimal number, by 2. So 42 by 2 means quotient is 21, remainder is 0. So note down in this way only. Again take the quotient as a number and divide it by 2, means 21 by 2 means quotient is 10, remainder is 1. Again 10 by 2 means quotient 5, remainder 0. And again 5 by 2 means quotient 2, remainder 1. And 2 by 2 means quotient 1, remainder 0. And 1 by 2 means quotient is 0 and remainder is 1. So continue this process till the quotient becomes 0. Continue this process till the quotient becomes 0. After that, you write down all the digits from the bottom to the top. After that, write down all the digits from the beginning, or write down all the digits from the beginning to the, or from the bottom to the top, starting from bottom to the top. That is the decimal equivalent of 42. That is the decimal equivalent of the binary equivalent of decimal 42 is 101010. So what is binary equivalent of decimal 42? Means write down from bottom to top. That is, the bottom digit is called as MSB, most significant bit, and the top digit is called as the least significant LSB. So write down all the digits from MSB to LSB, or most significant bit to the top least significant bit, or from bottom to top it is 101010. So the binary equivalent of decimal 42 is 101010. So next step is how to convert decimal to hexadecimal. How to convert decimal to hexadecimal number system, or how to convert a decimal number to equivalent hexadecimal number system. So take it as 5735, decimal 5735 to hexadecimal. So this is the explanation or process to convert from base decimal or base 10 to hexadecimal 16. So base 10 is 8039. So convert base 10, that is decimal number 8039 to hexadecimal. So we want to convert into decimal to hexadecimal, so that we simply divide the given number by 16. So the original number is 8039 divided by 16 means 16. 8039 by 16, the quotient is 502 and remainder is 7. Again divide, take the quotient as a number, that is 502, and divide the same number by 16, that is quotient is 6 and remainder is 31, and like that continue this process until the quotient reaches 0. The quotient becomes 0. So write down again the same thing. When we write all the digits from bottom to top, are most significant bit MSB to least significant bit. So the hexadecimal equivalent of decimal 8039 is starting from 1F67. So here you observe the remainders. The first remainder is 7, so leave it. Second remainder is 6, leave it. Third remainder is 15. So what is hexadecimal equivalent of 15 means capital F. What is the hexadecimal equivalent of 15 means capital F. Next remainder is 1. So starting from bottom to top, 1, 15 means capital F, 6, 7. So the hexadecimal equivalent of decimal 8039 is 1F67. So this is the process, or step-by-step process. So this is the step-by-step process to convert any decimal number or base 10 value into equivalent hexadecimal number. So what is the hexadecimal equivalent of decimal 8039 is 1 capital F 67. So how to convert from base 8 to base 10 means, that is how to convert from octal number system to decimal number system. How to convert from octal number system, that is base 8, to decimal number system, that is base 10. So example is convert octal 7 to 63. Convert octal 7 to 63 to equivalent decimal number system. So starting from, so here this is the table. This table you have to write on the paper on the examination. So first one is starting from the write down 8 power 0, 8 power 1. So the original base or index value is octal. So what is the base or what is the index for the given left hand side is octal. So 8, that is 8 power 0, 8 power 1, 8 square, 8 cube. Next one is 8 power 0 is 1, 8 power 1 means 8, 8 square means 64, 8 cube is 512. Next is starting from extreme left digit, right digit, that is first digit is 3, 6, 2, 7. 3, 6, 2, 7. So 3 into 8 power 0 plus 6 into 8 power 1 plus 2 into 8 square plus 7 into 8 cube. So how to write on the paper? 3 into 8 power 0 plus 6 into 8 power 1 plus 2 into 8 square plus 7 into 8 cube. So write in this way. After that multiply each and every digit, that is 3 into 1 means 3, 6 into 8 means 48, and 2 into 64 means 128, 7 into 512 means 3582.
ఫ్రెష్ అయిపోతే అన్నం తినేసి వెళ్ళిపోతారు కదా.
So you have to draw or write this table in the examination. So the original base is, so how to convert base 8 to base 10, that is octal number system to decimal number system. So the base 8 is, that is octal is base 8, that is 8 power 0, 8 power 1, 8 square, 8 cube. And starting from extreme right digit 3, 6, 2, 7. So 3 into 8 power 0 plus 6 into 8 power 1 plus 2 into 8 square plus 7 into 8 cube. Write down all these numbers and sum all these things. That is 3763, that is 3763. So how to convert base 8 to base 10, that is how to convert from base 8 means octal to base 10 means decimal. So take another example, 7 to 6, same example, 7 to 6 8, 7 to 6 8 octal 8 to decimal 10. So third conversion is from base 16 to base 2. So how to convert base 16 to base 2? What is base 16? Hexadecimal, and base 2 means binary. So how to convert the numbers from hexadecimal to numbers from binary? So why hexadecimal? Hexa easier to read and write than binary, and modern computer operating systems and networks present variety of troubleshooting data in hexa format. So this is another example. In hexadecimal to decimal means generally in hexadecimal to binary, or from hexadecimal to decimal we may take 4 bits as a group. Generally, when converting from hexadecimal to binary or hexadecimal to decimal, we may take 4 digits, 4 bits or 4 digits as a group, whereas in octal number system, that is base 8, we may take a group of 3 digits or a group of 3 bits. Generally, in octal number system, we may take 3 bits as a group. So fractions. So till now we may discuss only with the decimal numbers only, that is whole numbers or integral numbers. So how to deal with or how to do calculations with fractions or fractional part or decimal part. So number point or radix point, decimal point in base 10, binary point in base 2. So thank you. We may continue in the next class.